Intraterrestrials, the hidden world of deep subsurface life on Earth. The hidden world beneath our feet, unveiling the enigmatic realm of intraterrestrials. Imagine a life form that defies every conventional notion of existence, thriving without sunlight, breathing rocks, and surviving for millennia. Welcome to the mystifying realm of intraterrestrials, microbial life flourishing in Earth's deep subsurface. As we fervently search for extraterrestrial life beyond our planet, we often overlook the bizarre, unseen biosphere right beneath our feet. Karen G. Lloyd, a microbial biogeochemist at the University of Southern California, takes them on a captivating journey through her groundbreaking research in intraterrestrials, discovering the strangest life on Earth. This hidden world, starting mere feet below the surface and extending into the unknown, is teeming with life, even in the deepest, most inhospitable environments. The birth of a term, understanding intraterrestrials. Coined by biogeochemist Karsten Peterson, intraterrestrial describes life within Earth's crust. Lloyd's decades-long quest, however, reveals that these microbes can thrive without photosynthesis, leveraging geochemical reactions deep within the Earth. They can breathe rocks and live for thousands, possibly millions of years. From the ocean floor to volcanic depths and Antarctic permafrost, Lloyd has tracked these enigmatic microbes. A tale of two biospheres. Lloyd categorizes the subsurface intraterrestrial into two main types. The first utilizes chemosynthesis, converting chemical reactions into biomass without sunlight. The second feeds on leftover from photosynthesis that trickle down from the surface. Both types thrive on chemicals produced by rots under extreme heat and pressure, akin to how surface plants use sunlight. Advancing intraterrestrial research. Japan's ambitious Chiku ship, designed to drill through Earth's crust into the mantle, represents a significant leap in this relatively new field. Reaching the mantle, a 2,900-kilometer wide dense rock layer making up 60% of our planet, could revolutionize astrobiology. The implications are profound. If life exists in Earth's mantle, could any planet, no matter how inhospitable, harbor life? This raises intriguing questions about subterranean life on Mars and Venus. Radiation-loving bacteria. Meet Desulfurutus audax buter, a bacterium found 2.8 kilometers deep in a South African gold mine, which consumes the reaction products of pure radiation and water. This oddity holds the record for the deepest light discovered on Earth. The perplexing longevity of intraterrestrial life. Some intraterrestrials appear to be in stasis, yet are not. This phenomenon poses two crucial questions, according to Lloyd. Are these microbes adapted to remain dormant for millennia? Or do they simply persist without special adaptations? The bottom line, rethinking life beyond Earth. Lloyd's work offers a newfound appreciation for the depth of life on our planet. If such life exists here, why not on numerous extrasolar worlds, potentially informed, undetectable by our current methods? This sobering realization challenges our dreams of cataloging exoplanetary life, suggesting that some life may forever remain hidden, thriving in the unlikeliest of places. But here's where it gets controversial. Could our pursuit of biosignatures in the galaxy be inherently limited? Share your thoughts. Do you believe we're overlooking the possibility of widespread, undetectable life in the cosmos? And this is the part most people miss. The existence of intraterrestrial life on Earth opens up Pandora's box of questions about the universe's potential for life. How do you think this discovery should influence our search for extraterrestrial life? Join the discussion in the comments below. Earthquakes power subterranean life. New study reveals energy source for deep Earth microorganisms. Imagine an unseen force powering life deep within our planet. This is not science fiction, but a groundbreaking discovery that challenges everything we thought we knew about Earth's hidden ecosystems. Chinese scientists have uncovered that the sudden burst of chemical energy released during earthquakes can act as an alternative fuel source for microorganisms living far below the surface, essentially providing an energy lifeline that bypasses the need for sunlight. This compelling research, carried out by a team at the Guangzhou Institute of Geochemistry under the Chinese Academy of Sciences and recently featured in Science Advances, sheds new light on how deep Earth life thrives. In the shadowy realms beyond human sight, Up to 95% of Earth's prokaryotic organisms reside, constituting roughly 9% of the planet's total biomass. Unlike surface dwellers that rely on photosynthesis to convert sunlight into organic matter, these subterranean microbes have long puzzled scientists with the mystery of how they capture energy in an environment devoid of light. The researchers simulated fault movements several kilometers underground and observed that when rocks fracture, they expose fresh surfaces with broken chemical bonds. When these new surfaces come into immediate contact with water, a notable chemical reaction ensues, producing significant amounts of hydrogen and hydrogen peroxide. This reaction triggers extensive oxidation and reduction cycles, particularly involving iron, which continuously releases electrons. Think of these electrons as the currency in an invisible power network that flows between vital elements like carbon, sulfur, and nitrogen, effectively establishing a subterranean power grid that provides a readily available source of energy for these resilient microorganisms. But here's where it gets controversial. If such chemical processes can sustain life deep within our own planet, could similar mechanisms be at work on other celestial bodies, such as Mars or Europa? This alternative energy pathway not only redefines our understanding of where life can thrive on Earth, but also has significant implications for future space exploration. The study suggests that upcoming missions searching for extraterrestrial life should focus on areas near fold zones where both oxidized and reduced substances are present, and these regions might offer the crucial conditions needed for life to exist. And this is the part most people miss. By looking into the hidden corners of Earth's crust, where seismic activity fuels life in unexpected ways, we are not only rewriting the textbooks on deep Earth ecosystems, but also opening up exciting new possibilities in our quest to find life elsewhere in the solar system. What do you think about this unconventional energy source? Could it revolutionize our search for life beyond Earth? Or are there alternative explanations waiting to be uncovered? Your insights and opinions might just spark the next big discussion. Earthquakes unleash hidden life. How rocks feed microbes deep underground. Imagine a world where the very ground beneath our feet is teeming with life, hidden from our view and oblivious to the sun's rays. It sounds like science fiction, but the reality is stranger and far more fascinating. Recent research reveals that the cracks in rocks created by earthquakes are not just geological phenomena. They are lifelines for entire ecosystems thriving beneath our feet. But here's where it gets controversial. These rock cracks, far from being lifeless, are actually microbial oases, rich in hydrogen and oxidants produced by the very forces that cause earthquakes. Researchers at the Guangzhou Institute of Geochemistry had simulated seismic conditions to study these processes, discovering that when minerals like quartz or basalt fracture, they release highly reactive free radicals. These radicals split water molecules, creating energy-rich compounds that sustain deep-dwelling microbial life, the deep biosphere's hidden circuit. Beneath the surface, a vast network of bacteria and archaea thrives, making up around 15% of Earth's biomass. These organisms have been surviving and evolving for billions of years, thanks to the tectonic shifts and microquakes that regularly fracture rocks, creating an environment rich in reactive surfaces. The broken rocks, with their peroxy bonds, release energy when disturbed, essentially flipping millions of nanoscale switches at once. The researchers found that just 4 hours of artificial fault movement generated up to 160 micromoles of hydrogen, far exceeding what's produced by other natural processes. Over a year, this translates to about 33.1 moles per square yard, enough to support dense microbial biofilms. Imagine a tiny microbe surviving on as little as 10 to the negative 12 watts per cell. Even a minor quake releases millions of times the energy a single microbe needs, briefly transforming scattered rock zones into nutrient-rich hotspots. But hydrogen alone doesn't fuel life. It needs an electron acceptor, and in this case, iron cycling plays a crucial role. The experiment showed that hydrogen atoms can reduce ferric iron, FeC, to ferrous iron, Fe2, while hydrogen peroxide converts Fe2 back to Fe3 in surrounding pores. This self-sustaining redox cycle enables certain microbes to extract energy from iron, essentially feeding off the rusting process. And this is the part most people miss. Tests on granite samples confirmed that microbes can thrive by transferring electrons from iron within rocks. Over time, slow weathering and chemical mixing smooth out the initial energy spike from a quake, allowing microbial colonies to establish, adapt, and spread. Borehole samples from the Canadian Shield revealed ongoing iron oxidation and reduction over several years, reinforcing the idea that life taps into rock fracture chemistry to persist. These deep energy cycles may be more widespread than previously thought. Earth's tectonic network could be littered with chemical hotspots, creating far more habitable zones in the crust than imagined. Rock cracks could be hiding life on Mars, Europa, and beyond. The implications of this research extend far beyond Earth. On rocky worlds like Mars, Europa, or Enceladus, where brittle crusts undergo stress from impacts, tidal forces, or cooling, similar geochemical processes may be occurring below the surface. Mars rovers have already detected iron minerals capable of switching between redox states, and orbital imagery shows vast networks of surface cracks. This study provides a quantitative framework to guide future missions. Instruments capable of detecting hydrogen, methane, or shifting iron states could narrow the search to these fracture zones, where chemical energy meets potential biology. In this view, the best places to look for Martian life might not be surface oases, but the dark veins of cracked rock beneath. Back on Earth, glaciers offer a striking parallel. As they grind over basalt, they also release hydrogen, providing energy for microbes in subglacial lakes. Whether through tectonics, landslides, or ice movement, mechanical stress appears to be a consistent driver of underground ecosystems. So next time you feel the ground shake, remember that beneath the chaos lies a hidden world of life, sustained by the very forces that shape our planet. And this is just the beginning. The more we learn about these underground ecosystems, the more we realize how interconnected our world truly is. What do you think? Is this the start of a new understanding of life on Earth and beyond? Let's discuss in the comments.